Greetings all. I'd like to talk to you about electrochemical loading. On the right-hand side of this first screen is the cell with which we did most of our work at SRI, both loading studies and calorimetric studies. I don't have time to go into the details, but if you're interested in pursuing this avenue, I very much suggest that you pay attention to the details of this cell. Every detail was thought through, experimented with, and proved to be valuable. We started with a hypothesis. There is an unexpected and unexplained source of heat in the deuterium-palladium system that may be observed when deuterium is loaded electrochemically into the palladium lattice to a sufficient degree. What is loading? What does it mean? How is it measured? I'm going to talk a bit about the electrochemistry of hydrogen evolution reactions. Question still on the table is loading necessary for the Fleischmann-Pons heat effect? What else is needed to see the effect? And I'm going to talk about SRI best practices to achieve loading and electrochemical low energy nuclear reactions. At the bottom, a note: is the loading requirement a threshold or a window effect? And does this requirement remain after initiation? There are many methods to measure the bulk average loading of deuterium or hydrogen into palladium. The electrical method is the one that we very much preferred. The advantage is in situ real-time access. The disadvantage is that we can really only use it for palladium and some palladium alloys. The resistance ratio loading functionality is not known for most materials. You can use electrical, physical, chemical, electrochemical, diffraction methods. Our primary method was resistance ratio, which I'd worked on for a decade before 1989, but as secondary methods, we used simply gravimetric weighing cathodes and hydrogen consumption in closed cells, and also stripping coulometry, primarily to calibrate the resistance ratio versus loading functionality. Excuse me. What we really want to measure is the overvoltage. The overvoltage measures the chemical potential closest to the surface, where I believe the scene of action is in the Fleischmann-Pons heat effect. This is what Martin and Stan used. Martin was an expert. I found this method problematic. There are a number of things that you need to pay attention to, but that really, I assert, is what you want to measure. Whatever, choose one. Most of us believe that condensed matter nuclear reactions occur at specific sites in the lattice. They're localized, individually small, and in totality account for a very small percentage of the total sample volume. And they occur preferentially near the loading surface. That is where the maximum loading occurs. It's where the maximum flux occurs. And the observed helium release, quantitative helium release, really indicates that the effect is occurring very close to the surface. There are also observations of hotspots from Spa Wars and other places. So, but how does the bulk average atomic deuterium or protium to metal ratio, the thing that we measure, how does that relate to the local loading at the postulated sites of nuclear reaction? We hope that it's monotonic, that is, as one goes up, so does the other, but there are effects of lattice defects. I've listed a few here. There are many classes of defect. A question on the table still is, are defects important? Are defects critical to producing the effect? And how does what we measure cause or facilitate nuclear processes? The important variable is clearly not the average DD or HH spacing. Kuhnen circulated a calculation which was largely irrelevant and wildly inaccurate, it turned out, but it's just contemplating D2 or D2O. The DD spacing in D2 and D2O is similar to or even closer than the DD spacing in a fully loaded PDD lattice. So we know that spacing is not the issue. We also know that the Fleischmann-Pons heat effect requires time at high loading, suggesting that the loading process is promoting a chemical process. Is the important variable chemical potential? This is probably the most studied reaction in electrochemistry. It's normally done to cause precisely the reaction that we cold fusion guys want, or guys and girls wish to avoid. The reactions are so well studied and so famous that they have names, and the names have faces, which I've put around the side. The central box shows the discharge of protons in acid medium onto the surface of platinum, a very well studied system. The Volmer reaction, a proton plus an electron produces an adsorbed hydrogen atom. The hydrogen atoms build up on the surface and freely move. If two hydrogen atoms meet each other under the right circumstances, they form a molecule which bubbles off, which is what hydrogen evolution reactions are intended to produce. There's a second reaction, which is really the sum of the first two, but the mechanism is slightly different. An adsorbed atom and a proton combine with an electron at the surface to produce a hydrogen molecule, which bubbles off. In the bottom set of equations, I've written for an alkaline system, non-acid, and for palladium, not platinum. We're looking to promote the step arrowed in purple, the loading step. This is what palladium introduces that platinum does not. The possibility of loading atoms below the surface into an absorbed state. The Volmer and Tafel reaction, the Tafel reaction is exactly the same. The Volmer and Hairovsky reactions proceed with H2O, water, as the reactant, but otherwise similarly to acid. Much of what I know about electrochemistry was taught to me by people in this picture. At the end of the Second World War, John Bockris started a school of physical electrochemistry at the Royal College of Science in London, which later became Imperial College. In the back row, circled in green on the left, is my PhD supervisor, John Tomlinson, who is one of John Bockris's first tranche of students. The two remained very close. I did my PhD in Wellington, New Zealand. John Bockris at that time was in Australia. So the two saw each other very often. I had many hours of fascinating discussion with John Bockris. In the back right, circled in green, is Martin Fleischmann, who was part of that group. There are two other famous electrochemists in this picture. In the front row, second from the left, Roger Parsons, and second from the right, Brian Conway. All of the people whose names I've mentioned became important in my life and very important in cold fusion. My Bible of physical electrochemistry was John Bockris's Modern Aspects, first published in 1973, 2 volumes, 840 pages, very dense reading, very well worth attempting if you're interested in the electrochemical method. Some of what I learned from Bockris and his students, it's not for the faint-hearted. There is a tendency to think that electrochemistry is easy. I've watched people fall into that trap many times. It isn't easy. There's a scrupulous avoidance of impurities, and we used to distill our water 3 times in a procedure that had been, road tested. We used borosilicate glass or quartz. There was a special cleaning and polishing protocols were developed. Fanatical attention to surface preparation. Unfortunately for us, or possibly not, rods and wires are hard to polish, and some have succeeded in cold fusion by accentuating the surface roughness. Basically, what we're trying to do is control the kinetics and control the surface to promote the loading reaction. Water going to an adsorbed species, going to an absorbed species. Facilitate the kinetics of the Volmer and loading reactions, inhibit TAFL, and even more strongly inhibit Hierofsky. I will tell you why. The extremely high permeability of palladium makes the conditions of the metal bulk of paramount importance. The bulk talks to the surface talks to the bulk. They are not decoupled, they are closely coupled. The bulk microstructure is therefore critical. Crystal orientation, grain size, grain boundaries, alloying, included impurities. An important paper on this is referenced below by NRL, and extensive work was done at ENEA by my good friend Vittorio Violante and his group. There's an issue of surface propagation of cracks, which I'll talk about shortly. Apologies for this drawing. I didn't even draw it. I stole it from the internet, but it's the analogy of the leaky bucket, which I've always used to describe this system. Volmer is the current. It's the water pouring into the bucket. TAFL and Hierofsky are taking adsorbed species away. We want the monolayer concentration of the hydrogen adsorbed species to build up to high chemical potential to promote high chemical potential of the absorbed species. The H-ab is a loaded hydrogen atom. This is what we're attempting to promote. There are a number of classes of defects in solids. Internal voids, for example, if the TAFL reaction can occur on the inner wall or the outer wall of this inner void, then we will produce hydrogen molecules in the void at a pressure equivalent to the chemical potential of the hydrogen absorbed into the lattice. There are grain boundaries which act as rapid conduits of hydrogen out of the system, so it deloads our bucket rapidly. We've been able to accommodate that problem by coating the ends of grain boundaries with aluminium or silicon. I found no other way to stop down grain boundaries. It's also surface cracks. If the void fills up with a high pressure of hydrogen, there's a possibility that the lattice will crack, that the crack will propagate to the surface, and the hydrogen will spill out through the crack. Alloying helps somewhat. Lithium does this naturally, and we've added boron, which seems to help with this problem. But you can always fill a leaky bucket by increasing the fill rate, which in this cartoon is the current I. But Hierofsky causes deloading. Note that Hierofsky reaction takes an adsorbed species and an electron and produces a hydrogen molecule. It costs you electrons and it steals your loading. So the Hierofsky reaction is very much to be avoided. And the loading versus current density is projected to exhibit a maximum. Dennis Craven's promoted what I call the Craven's maxim: load cold and slow, exercise hot and hard. You want to get the system very well loaded before you try and initiate your excess heat reaction. But loading is a dynamic process. Low energy reactions are a dynamic process. For loading, we need to control all phases of the system: the electrolyte, the surface, the bulk, and the current time profile, which is a thing we have most control over. In the electrolyte, generally organics are bad. Most cations that discharge onto the surface are bad. We can use surface recombination poisons to inhibit Tafel and Hierofsky reactions. Heavy metals, lead and mercury may be good, but the timing is important and the concentration of these is important. Surface condition. An electrochemist would polish. In our case, we found that etching was effective. Crystal orientation is effective. Highly polished surface is probably more reproducible and better for electrochemistry, but I'm not certain that it's better for cold fusion. The bulk metallurgy needs to be controlled. Dissolved impurities, inclusions. The skills of the metallurgist are very heavily in demand, but really what we need to do is to prevent crack formation or prevent crack formation above a critical dimension. Current density starts slow, and the way we control the surface is by judicious current reversals to re-establish the surface. A surface that works is sensitive to preconditions, but the surface changes with time. What works for Fleischmann-Pons heat effects are not mainstream electrochemical thinking. The dynamics are crucial. Dave Nagel in this workshop told us that the materials change during LENR due to loading. That's true. My assertion is that all aspects of the system change, importantly with time and charge passed. The electrolyte present after hundreds of hours of intense electrolysis is not the same as the original electrolyte. A surface that produces excess power is not the same as the original surface. In situ surface reconstruction is necessary for the electrochemical Fleischmann-Pons heat effect. That last statement is my assertion. I might find some arguments in the electrochemistry community. The palladium volume near surface that produces excess power is not the same as the original material. Considerable time is needed for bulk phase reconstruction. And a key agent of change, the one that we can control, is the current density time profile. This is the profile that we evolved to and then used over and over and over again. You start slow. Start your electrochemistry at 2 or 5 milliamps per square centimeter, and then step logarithmically to 5, 10, 20, 50. By the time you get to 20 or 50 milliamps per square centimeter, if everything looks good, the electrode is responding nicely to the current steps. It has achieved a loading on the right-hand side of the resistance maximum. Looks good. At that point, we will initiate a very slow current ramp. The ramp shown in this graph is 5 milliamps per square centimeter per hour. So the current density increases 5 milliamps per square centimeter every hour. If there's no excess power at the end of this first ramp, and there usually is not, then we force a surface restructure by a current reversal using an anodic voltage clamp. So we make the cathode and anode, we strip off the surface that is presently there and presently not doing what we need it to do, dissolve it back into the electrolyte, and hope when it's redeposited, it redeposits in a more advantageous way. Put a voltage clamp on 800 millivolts, typically because you don't want to make palladium oxide. And we calculate the current time for as the charge needed to deload the cathode just to the left of the resistance maximum to a loading value of about 0.75. And you repeat this procedure over and over and over again until you get excess heat, in which case you stop and study it, or the cell fails. Fleischmann and Pons typically did not give up on a cell before 3 months of electrolysis, and we've certainly run cells for 3 months, although we didn't always, but you must be patient. This is the resistance ratio loading curve that I spent so many years working with. 2 attempts to characterize this curve. One in orange or gold is our attempt, and the red one is a very nice work by a group of Zhang, and Zhang. I disagree with the position of the peak a little bit and the value of the peak a little bit, but it matters very, very little. I'm interested only on the right-hand side of this bump, where the resistance is decreasing rapidly with atomic ratio. The blue boxes are data obtained by Baranovsky at extraordinarily high gas pressures. So D2 gas was introduced at high pressure, and the loading was determined by the amount of hydrogen lost from the gas phase, or deuterium lost from the gas phase. As you can see, these pressures are extreme, gigapascals. The red filled point, is the maximum loading that we obtained at SRI, and the pressure that it corresponded to, according to Baranovsky's data, was 23,000 atmospheres. So if there were a void inside that piece of palladium, and the Tafel reaction were allowed to occur on its surface, the pressure in that void would be 23,000 atmospheres, 2.4 gigapascals. The yield strength of palladium is 30 megapascals. I don't know what it is for PDD, but I doubt that it's very different. Either way, we've greatly exceeded the yield strength, suggesting a possible problem. Most many or most ramps ultimately exhibit deloading. That is, you cannot do this over and over again. The electrode gets tired, the surface becomes sufficiently unsuitable, unsatisfactory, that loading cannot continue. This could be a surface effect. It could be void pressure cracking, which I'll speak to in a second. But loading is critical, but so are time, current density, and absorption flux, and these are interdependent variables with somewhat conflicting requirements. With appropriate normalizations, we can compare multiple current ramps. We're looking for what is good and what is not good. In a good situation, which I call mode A behavior, and I have 8 examples in this slide, the resistance decreases linearly as the current density increases logarithmically. Here the current densities are normalized to 33 milliamps per square centimeter. So the right-hand side of this plot is 3.3 amps per square centimeter. But this log linear behavior can maintain up to 1 amp per square centimeter. This is the behavior that we would expect for electrochemistry if the Hairovsky reaction was effectively suppressed. We published this, Fran and I, in the ICCF24 proceedings. I invite your attention. We have another set of 8 ramps with this normalized plot. The initial trajectory is the same, log linear decrease. But at a certain point, the resistance heads up. The electrode gives up. It says, I can't do this anymore. I'm going to deload, and that deloading is precipitous. Sometimes this can be seen as visible bursts of bubble streamers. These have been studied and shown to be, in some cases, supersonic. What I am arguing here is that this is a condition with an internal void. The void has been pumped to a very high pressure. I indicate the pressures in this orange bar labeled in red. The pressure, Baranowski pressure, equivalent to that resistance ratio. These are big numbers, 100 megapascals to 300 megapascals. Remembering the yield strength of palladium is around 30 megapascals. So I claim that this is evidence of physical lattice disruption from the inside. We've seen this directly with purpose-made voids, for example, Arata's double-structured cathodes, in which we have measured enormous pressures directly with a pressure gauge, and indirectly or disruptively by exploding, not intentionally, these closed voids. But the pressures inside are real and huge. Closed internal voids can break the lattice if the pressure is not relieved. Do we need to avoid voids large enough to permit D2 formation? If the surface is sound, the current density promotes loading, but the bulk can sustain loading only if the lattice is sound. This might be a problem or an opportunity. Some ramps do not exhibit this rapid deloading phenomenon. Some cracks apparently can be healed. Mode B behavior can transition to mode A. You see our ICCF7 paper for more details. Ed Storms hypothesizes that cracks of certain dimensions are the sites of nuclear action, so maybe size matters. I think more generally, are narrow channels the sites of nuclear action? Lipson and Miley spent much effort loading dislocation cores, which are linear channels inside the palladium lattice. Andre Lipson incorporated carbon nanotubes into a palladium matrix and used that as a cathode. We observed this effect at SRI and at Energetics Technologies Incorporated. Such structures do exhibit excess power. And Mike Staker's superabundant vacancies, which I'm very interested in, single atom channels. So I think it's distinctly possible that linear channels can promote the excess heat effect. You need to preserve a sound bulk structure and construct a surface that will load at high current densities. I'll leave you with, I'll give this to study at your leisure. I kept this chart beside me, pinned to the wall during all of my active experimental years. It's SRI's first 25 experiments. There's a huge amount of information on this chart. Those interested can inspect it at their leisure. It does repay close attention. But two of these experiments were done in closed mass flow calorimeters, all pressurized with D2, except one of the experiments was a light water experiment. Most of them were Engelhardt Lot 1, a single lot of palladium with which we obtained most successful results. There are some initiation times. The minimum initiation time on this set of experiments is 184 hours. No excess power was observed before 184 hours. The highest number is 684. In one case, we went 684 hours of electrolysis before excess power was first produced. The current threshold holds minimum 120, maximum 884 milliamps per square centimeter. About half of these showed excess power at the greater than 3 sigma level. But there's a section in there, more than 1 year, with no measured excess power. We this actually induced a certain level of intestinal fortitude, both on our part and our sponsors. But fortunately, this was followed by a series of 13 experiments. All except 2 exhibited excess power greater than 3 sigma confidence. The 2 that didn't, one was a light water experiment, and the other was aborted due to an electrical failure. Well, I hope I haven't frightened you away from the electrochemical pathway. It's complex, not fully understood, but it can and has been done. I assert that electrochemical loading is superior to any other form. Its ability to create high chemical potential with minimal apparatus, and importantly, to simultaneously permit high absorption flux. I believe that both are necessary to produce excess heat in the modes that I've studied. You need to achieve and maintain a conducive electrochemical interface by controlling electrolyte purity, but you always, I think, are going to need to do surface reconstruction, dissolve the surface and redeposit it, hopefully in a more advantageous way. You need to create or inherit, if you're lucky, bulk material with a low void population or voids with inhibited walls that do not allow the Tafel reaction to occur and cracking to occur to the surface. Other ways may be possible. Francesco Celani, a man who I've learned a lot from, uses axial current stimulation of surface-treated long, thin wires, apparently very effectively. Ed Storm's gas loading of purpose-fabricated bulk materials where cracks are said to be critical, where I've been critical of cracks. And Akito Takahashi and his fellow countrymen, gas loading of nanomaterials, very interesting work, avoiding electrochemistry. I'm very grateful to a large number of people, my mentors, the SRI initial team, particularly Fran and Susan, who stuck with us through thick and thin, my program managers and sponsors, particularly Tom Passel at EPRI and Bob Nowak at DARPA. Had many collaborators over the years, many good people, not all still with us. I draw particular attention to Peter Hagelstein at MIT, Mike Mielich, NRL or in the Navy, and Vittorio Violante and his team at ANEA. I don't have time to do justice to everybody on this list. I suspect that I've forgotten some to whom I apologize, but if you're on this list, know that I love you and that you all made it possible. For those who are still with me and interested in digging into electrochemical kinetics of the DPD system, I suggest electrochemical impedance spectroscopy. This was my primary field of expertise before March 23rd, 19, and still my most cited publications. Small amplitude perturbation, you can interrogate electrochemical kinetic, mass transport, and surface conditions. I worked on this in LENR with Vittorio Violante and Tony Legata. And Herb Dardik's superwaves, which I don't have time to get into. This graph on the left, or set of graphs on the left, is intrigued Martin Fleischmann. The bump at the bottom shows decreasing resistance with decreasing frequency. The minimum frequency here was, I think, 1 millihertz, but this is a sign of positive feedback, and Martin was very interested in positive feedback. And Martin and Stan came and stood in front of this graph after my talk at Salt Lake City in ICCF1 now called, and was was very, very interested in it for very good reason. I invite you to pay attention to this. And if you're interested in pursuing the electrochemical loading method, I advocate the resistance ratio and electrochemical impedance techniques. Thank you for your attention.